Welcome everyone in this video lecture series on data structure. Today we will cover the topic insertion sort. For better understanding of this topic, you must have the fundamental knowledge of sorting concept and you should familiar with sorting algorithms like bubble sort or selection sort. I have already covered these topics in my previous video lecture. Link for those videos are given in the I button and also in the description section. So let's begin the concept of insertion sort. So just like bubble sort or selection sort, insertion sort is also a comparison-based sorting algorithm, and it is inspired by the way we sort playing cards in our hand. So whenever we want to play any card game, some person distribute the card and we all store our cards in a sorted order in our hand. So why it is required? So that we can choose the most appropriate card during playing in less time. Fine. So let's say we have one hand of sorted card and we just received another one. So in my hand, let's say there exists 3, 4 and 8 cards. Okay. So these 8 cards are already sorted, but now I received a new card which contains 5. So forget about the phase symbols. Okay, just concentrate on the numbers. So previously there was 2, 3, 4, 6, 7, 8, 9 and 10, and now we have 5. So what do you have to do? We have to place this card 5 in between 4 and 6. So we should make some space in between 4 and 6, and then we can place this card in that position, right? So in this way, we can maintain the sorted order. Now, question is that how do we get the sorted hand in the first place? The initial sorted hand, right? So the answer is that whenever we receive the first card, it is already in sorted order. Because we have only one data, so it is always sorted. Now, whenever we will receive the second card, there exist two possible positions for that new card. One is before the first card, another one is after the first card. So based on the value, we have to insert the new card in its appropriate position. So again, my hand is sorted. Now, if I receive the third card, now the number of possibilities is 3. Because we can place the new card at the very beginning or in between existing 2 cards or after the last card. Fine. So that means there exists 3 possibilities. So based on the value, we can place that card in its appropriate position. So we have to continue this process, and every time we will insert the new card in its appropriate position and we will maintain the sorted order of my hand. Okay. So the same approach is used in case of insertion sort for computer-based sorting. Okay. So initially, I want to explain you the overview of this sorting with some raw data. Then we will check the internal details and then we will go for the algorithm. So let's say we have 6 data starting from 8, then we have 4, 1, 2, 3 and 5. So what is our objective? We want to sort this data in ascending order. So I can say that there exists one boundary in my data which split the entire array into 2 halves. In the left hand side of the boundary, we must have the sorted subarray. In the right side, we should have unsorted subarray. So initially, in my sorted subarray, there must be only one element. So as I explained you earlier that if we have one element within my array, I can say my array is already sorted. So next time what you have to do? We have to push this boundary towards the right hand side. So when this boundary shifting is possible, we have to consider the first element in the unsorted array. If we place this element in the correct position, then we can push this boundary towards the right hand side. So value 4 is less than 8. So what you have to do? In the first position, we have to store 4. Then we should have 8. Now we can push this boundary. Then we have value 1. So it must appear prior to 4. So if we able to store this value 1 prior to 4, then we can push this boundary. Now we have 2. So we have to place this value in between 1 and 4. Similarly, for the value 3, we must store it in between 2 and 4. So here you can see in between 2 and 4, we are able to store this value 3 and we are able to push this boundary. Now in my unsorted subarray, there exists only one element. And what is the element? It is 5. So we must place this element in between 4 and 8. If we are able to do this thing, ultimately we will get the sorted array. Fine. But what is the problem? Just like hands of card, it is not possible to create empty space in between two elements within an array. So if it is not possible, then how we can place the initial element from my unsorted array to the sorted subarray? So the solution is shifting operation. So whatever I explain here, this is just the oversimplified representation of the insertion sort. So here I just told you that this element 2 is present in my unsorted subarray. Okay, this is the first element of my unsorted subarray. I have to place this element in between 1 and 4. But I haven't explained you how to place this number in between 1 and 4. So that is done with the help of shifting. So here I take one arbitrary snapshot of insertion sort where we have already pushed the boundary towards right hand side. So in my sorted subarray, we have 4 elements, and in my right hand side unsorted subarray, we have 2 elements, 3 and 2. So in the next iteration, we are supposed to place this 3 in its correct position. And what is the correct position? It should place in between 1 and 4. So what I have to do? Basically, we should keep a copy of this number 3 within a temp variable. Fine. Now, we will iterate over the sorted subarray from right hand side to left hand side. So if we encounter any element which is greater than 10, what we will do? We will shift that element in the right hand side. Because this number 3 will be placed before 8, so we need some empty space. Okay. So for that purpose, what we will do? We will place this 8 in the next position. So that means we can conclude one thing from here, that if we place 3 prior to 8, it must shift one place in the right hand side. So that's why we should copy the value 8 in the right hand side, and then we will visit the next element. So next element is 6. So 6 is also greater than 10. So what I have to do? We have to shift this element in the right hand side. Then the next element is 4. 4 is also greater than 3. So again, one shifting is required. Now what is the next element? Next element is 1, which is less than 10. So that means after 1, we must place this value 3. So this is the terminating condition. So after that, what we have to do? We have to increment the value of j, and in the jth position, we can store the value of 10. There may be another terminating condition for this iteration, that could be the end of the sorted subarray. So if we reach to the boundary, then no more shifting is required. In that case, again, we will increment the value of j, and in the jth location, we will store the value of 10. After this, what will happen? We can shift the boundary one place towards the right hand side. So in my left hand subarray or in my sorted subarray, we have now 5 elements, and in my right hand subarray or my unsorted array, there exists only one element. So if we repeat this same process, then we can place this element 2 also in its correct position. So now I want to formally introduce this algorithm. It will accept one list A, which will contain n number of elements, and this algorithm supposed to create one arrangement of A, so that we can say that the elements of A are in ascending order. We need one iteration by which we will push the boundary. Which boundary? The boundary which segregate the sorted subarray and unsorted subarray. In my initial state, there should be one element in my sorted subarray. How many elements present in my unsorted subarray? N minus 1 elements. So we have to push this boundary how many times? N minus 1 time. So that's why we need one for loop which will start from 1 and it will ends at n minus 1. So here I am considering that array index starts from 0. Next, what do you have to do? Within a temporary variable, we will copy the value of ai. Okay, so what is the meaning of ai? So this is the first element in my unsorted subarray. After that, what do you have to do? We have to iterate over the sorted subarray from right hand side to left hand side. So if I points to the first element in my unsorted subarray, so the sorted subarray must ends at I minus 1. So that's why we said the value of j is I minus 1. Now what we will do? We will iterate from right hand side to left hand side in my sorted subarray. Now how many times we have to iterate? It depends, right? So if we get any element which is less than this key or temp, we will stop. Or if we reach to the boundary, we will stop. So in case of while loop, we have to provide the positive logic. So that means if boundary is not reached and the element which we are getting is also greater than key, then we will execute the while loop. So in the while loop, what we will do? We will perform the shifting, that is a j plus 1 equals to aj. Then what we have to do? We have to decrement the value of j. Now this while loop may get terminated due to two reasons. First reason, it may reach to the boundary, the left hand side boundary. That means no element is present in my sorted subarray, or we already reached to a element which is less than the key. In the both the case, what you have to do? We have to store the key in the next position. So that's why we can write a of j plus 1 equals to key. So if we repeat this process n minus 1 time, what will happen? We are able to push the boundary from the first position to the last position. So in that case, there will be no element in my unsorted subarray. All the element will be present in my sorted subarray. So ultimately, we will get the sorted array. Fine. So this is the algorithm of insertion sort. I hope now you can understand and you can able to implement this thing. Let's talk about the time complexity. So best case time complexity when data is already sorted. So if my data is already sorted, it will not execute my while loop, right? Because in the first place, we will get one element which is less than key. And that's why it will not execute the while loop. So ultimately, how many comparisons are required? Only n minus 1 comparisons. And if the while loop execute 0 time, so number of shifting will also remain 0. In that case, time complexity will become order of n. And what is the worst case time complexity? We will get the worst case time complexity if my array is reversely sorted. Let's say I want to sort the data in ascending order, but I get the data in descending order. In that case, what will happen? In the first iteration, we have to perform one comparison and one shifting. In the second iteration, we have to perform two comparisons and two shifting. So in my n minus 1th iteration, we have to perform n minus 1 number of comparison and n minus 1 number of shifting. So ultimately, we will get this count in form of n into n minus 1 by 2. Basically, we are getting 1 plus 2 plus 3 dot 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 up to n minus 1. So we know that summation of first n natural number is n into n plus 1 by 2. But here we are getting n minus 1. So it will become n into n minus 1 by 2. And this will remain same for my shifting. So ultimately, we will get the cost polynomial as a degree 2 polynomial. So time complexity will become order of n square. So some frequently asked question from this algorithm. First one, is it a in-place sorting algorithm? Answer is obviously yes. No auxiliary array is required and some additional space are required, but that is constant. It is not depend on the problem size. So that's why it is a in-place sorting algorithm. Is it a stable sort? Answer is yes. Equal elements will maintain their original relative order. So that's why it is a stable algorithm. Is this algorithm adaptive in nature? Answer is yes. So if we provide sorted or almost sorted data, then the number of comparison and number of shifting will be very less and it will become almost order of n. Fine. So that means pre-indexing of the elements affect the performance of this algorithm. So that's why this is adaptive in nature. Where insertion sort is suitable, if we have very small amount of data or data is nearly sorted, in such scenario, it will provide a very good performance. Real world use case. So there exists many hybrid algorithm where more than one sorting paradigm is used. In such scenario, we may use the concept of insertion sort. Some examples are intro sort or team sort, where we use insertion sort. So all these algorithms, hybrid algorithms, are mostly divide and conquer in nature. So when problem size become very small, they use insertion sort to sort that small problem. Okay, so this is one very good real world use case of this algorithm. Implementation, so signature for the implementation will be same as for the previous two algorithms, bubble sort and selection sort. So we need one function to create the array, one for the scanning, another for the printing. And in my insertion sort function, we will pass the array, its size, and we may use one Boolean flag. So this flag will decide whether this function will show the intermediate results or not. Okay, so that's all in this video lecture. Thank you.